Thank you very much. Thank you everybody for joining today. Let's get right into the presentation, which is avoiding VNF starvation in mobile networks using SmartNICs. So let's talk about bottlenecks. I like to use the water analogy when talking about this subject. I think it's kind of intuitive. Everybody knows that when you have a pipe and you try to get water to flow through that pipe, it's only going to flow as fast as the narrowest point in the pipe. If you have a clog, it's going to slow things down, and you're going to get a drip instead of a nice stream of water. Obviously, in networks, this happens as well. When you have a network set up where you have a bunch of different hops, whether they be physical hops like switches or NIC cards, or virtual hops like virtual switches or virtualized networking functions, and one of those is slow, it's going to slow down the entire network. So this is a critical point. It might be obvious, but it's very important to understand as we move into the era of widespread deployment of NFV, right? And operators are investing, incredible amounts of money building out the infrastructure for these NFV data centers with very expensive compute resources, very expensive networking equipment. And if the performance is being held back by, something in that chain, that's really not a good use of those resources. So let's talk about where these bottlenecks could occur. There are various points in the NFV data center that are of interest. Certainly things like the network switch is one point. The network interface card that's in the compute node connecting the server to the network switch is another point. And then inside the server itself, you have typically some form of virtual switching layer as part of the NFVI. And then you have, of course, your applications or your virtual networking functions. So a bottleneck, can occur in many different places potentially, right? But let's talk about where they're more likely to occur than not. So if you look at network switches, hardware, this is a well-known technology that's been around for many years. It's purpose-built, typically on custom silicon, that's designed to operate at wire speed across all packet sizes. That's pretty much a given for any type of switch, whether it's a spine switch or a top-of-rack switch in the data center. So this is typically not a bottleneck in the NFVI layer. Moving into this compute node, and we start to look at the virtual switch. Today the virtual switch is mostly software-based, the implementations that are out there. And we know that software, implementations struggle when the packets get small, the packet rate goes up, there's a limited amount of instructions in a server. Oftentimes the virtual switch is a bottleneck in the NFVI. And then the endpoints, the applications or the virtualized networking functions, today they typically are draining, the traffic or accepting the traffic that is being delivered to those endpoints by the virtual switches, much like, the river delta is draining the river into the sea. But of course, you can imagine that if you were to speed up the virtual switch and make it faster, if you had a flood, and that could overload the endpoints or the tributaries, and those could become the bottleneck in the network. And we'll talk about that a little bit more as we get further into this discussion. So let's go down a layer and start to parse into the compute node and talk about the architecture of the compute node. Typically, again, today you have a standard NIC, network interface card, which is just doing basic functions, doing things like moving packets back and forth, RX, TX, DMA, Ethernet packets. And also, of course, well-known basic offload functions, acceleration functions, if you will, of things like checksum calculations, large segment offload, receive side scaling. These are well-known offloads that are implemented in virtually all network interface cards today. On the compute node, on the server side, now in an NFV context, you have the virtual switch. So that could be any flavor of virtual switch. It might be something like OpenV switch. It might be VPP, some form of vRouter, a data plane, for instance. And that's running in the host. It might run in the hypervisor. It might run in user space. There's different implementations, but they're all software-based. And then you have the endpoints, the VNFs. In terms of the packet flow, you see that typically, you have packets obviously coming in, being pushed through the virtual switch, making the virtual switch making a steering decision based on the rules and hitting the appropriate target VNF. Packets in a gateway application would be coming back out and going to the network. It's possible also the packets could be terminated in the VM or dropped in the VM, let's say in a firewall application. And then, of course, we should consider the service chain scenario where packets are going from one VM to another in a service chain. And, of course, between hops in the service chain, they need to go through the service forwarder in the virtual switch. So let's consider the case of VM starvation, right? VM starvation occurs when you have a load in the form of the VNFs that can process more traffic or are ready to process more traffic than the virtual switch can deliver. So this shows a scenario where you have a 24-core compute server. 4 cores are allocated towards the virtual switch. 20 cores are allocated towards the VNFs. And that could be, one large VNF, 2 medium VNFs, a bunch of small VNFs. Doesn't really matter. The point is that those VNFs, the processing capability is roughly proportional to the number of cores, and we're making an assumption here that 1 million packets per second per core is what the VNF, this particular theoretical VNF, could process. The virtual switch, we're assuming that that's optimized. It can process faster, can do about 3 million packets per second per core. I think that's in line with some of the numbers that have been discussed this week at the conference for different types of virtual switches. And you can see, obviously, in this case, you have a bottleneck, right? You can only do 6 million in and 6 million out through the virtual switch. That adds up to 12, which is the capacity of those 4 cores. Yet the VNFs, can do a lot more. So you're underutilizing or starving those VNFs effectively is what's happening. So let's look at the case where you try to solve the problem by equalizing the vSwitch processing throughput with the VNF capabilities. And of course, you can do that by allocating more cores to the virtual switch. And you can roughly match the virtual switch throughput with the VNF throughput. But in this case, we're showing that in this scenario, you need 10 virtual switching cores compared to 14 VNF cores to get that kind of matching. And so you've now effectively dedicated almost half of, over 40% of your CPU to the virtual switch processing. So that's also not a good utilization of the infrastructure resources in the data center. So what we're showing now is taking the virtual switch and moving it into a SmartNIC, and that's what a SmartNIC is, right? It's able to do these functions like virtual switching that involve, match action forwarding in the case of OVS, but can also involve more complex functionality like QoS and security rules and things like that. So this is a SmartNIC implementation that we're showing now, where effectively, we're getting matching between the virtual switch and the load, the VNFs. There's no VM starvation or VNF starvation in this case. And the packet processing is done primarily in the SmartNIC, which is the virtual switching data path. And we only need some minimal CPU resources in the server to manage and control the virtual switch. So one core is shown as being utilized for that. Okay, so this is a good way to open up the bottleneck and maximize the server resources. And the point here of this chart, we all know speeds are increasing. This shows in some detail the port speeds going into the server. So the example that was shown was at 25 gigabit Ethernet. Obviously we're going to higher bandwidth, 40, 50, 100 gig Ethernet going to the server over the next several years. So this problem is going to get a lot worse with the increasing port speeds. Now, the other issue is not just more packets per second, but more work per packet, right? There's more complexity that's being added to the data path. So we have, things like we mentioned service chaining, right? Where you need to potentially make a decision on how to forward the packet in a service chain. Encapsulation formats to support that, like VXLAN, GPE, network service header, mobile VNF tunneling protocols like GTP, need to be understood and parsed. In some cases, we need to do lookups on fields in those packets. If you want to do something like TEID load balancing with GTP, you need to parse, do a lookup, and so on. So this is all extra work that has to happen inside of the virtual switch. And that adds to the load and reduces the processing rate in a software-based virtual switch. The other things to note here are things like ACLs for security, and that's both stateless and stateful. So Contract is an example of a stateful connection tracking subsystem that's used for security. Again, that will slow down the server-based processing. Network address translation also requires more manipulation, substitution of IP address, sometimes port information. And finally, in-band network telemetry, there's been a lot of discussion about that, where you can insert metadata into packets to track things like latency, jitter, and timestamps and things like that. So again, more manipulation, more operations per packet, and that's basically increasing complexity. So with that, I think Tapio is going to talk a little bit about complexity.
Thanks. Yeah, okay, thanks. So as a background for this presentation, I did a little exercise and I looked at the life of a packet. Like, let's say, I wanted to call this the day in the life of a packet, but actually it doesn't take that long, so I call it the millisecond in the life of a packet. So what I did was I took one of our OPNFV systems in our OPNFV lab, and I took an IP packet, of course, and actually set up a system where I have two virtual machines, and then I have a router so that I can SSH to the virtual machines and just set up two networks between the virtual machines. And what I do is I do the simplest thing possible. I have two Ethernet interfaces on the two instances, and I just send a ping package from one virtual machine to another virtual machine. And I just actually did it by hand, sort of wrote down on a piece of paper like what are the, all kind of information and what kind of MAC addresses and IP addresses and so forth, and sort of trace through everything that happens and try to understand it. So I'm going to show it now, and it's a little bit complicated, so I'll go slowly. Is it okay I spend the rest of the time explaining the packet?
Absolutely.
No, I will skip a few details. So anyway, so that was the first approximation, was that you have two instances. Of course, what you have is you have physical hardware. These are virtual machines running on a physical hardware. You have physical NICs. And then one important thing is, besides the IP addresses that I save up, you also have the MAC addresses. And I'm just sort of copied it here because I'm going to need those MAC addresses a little bit later. And then you have this famous virtual switch. So the next level of abstraction is that this packet comes from the virtual machine, it goes to the vSwitch, it runs on the physical hardware, it goes to the physical NIC, and so forth. And then this system actually was the one which uses the kind of like old-fashioned way of using Linux bridges to implement the IP tables rules. So if I go, and now I got tired of drawing this diagram, so I just took half of it. So the Ethernet interface inside of the virtual machine is connected to a tap interface is connected to Linux bridge. Other end of the Linux bridge is connected to brint, which is then connected to brton, and that's connected to the NIC. So this is one way of looking at it, and then another way is that actually the OpenV switch implements it so that it doesn't have these sort of individual bridges, it's just a sort of a data plane. So then when you get the packet arrives from the Ethernet interface, go to tap interface, go to Linux bridge, it goes to the data plane, and then it's connected to a VXLAN tunnel that is implemented, and then it goes out to the NIC. So here's the packet, you see it again. So this is for TCP dump from the packet. So it's an ICMP packet with the ping, source MAC address, destination MAC address, Ethernet type IPv4, so forth, minimum size. First thing I do, I looked at the Overflow flows, and you get this very long list. So I'm actually highlighting the one that it actually matches. So it matches this rule. It jumps to the next table, table 25. That's the action here. And then on the table 25, it says normal. So it doesn't actually tell me what it's going to do, except that it does the normal thing that usually Linux does with the IP packet. So I can then look at the data path in the IP, in the OBS, and I get this list of actions. And again, I'm actually highlighting the one that shows what is actually happening. So it's matching the source address, destination MAC address, the IP type. It's updating the counters. It's counting how many packets you get through, how many bytes you get. It's actually, I think, tracking sort of how long this flow stays alive. And then it does something with it, puts it into a tunnel, so it sort of does a little bit rewriting, it puts the VXLAN tunnels on it, and so forth. Does it make sense to do this in software? I don't know. It sounds like it's going to take a long time. But we only had one rule. Well, what about security groups? So of course, I mean, I had these Linux bridges, and now I think I got tired of this presentation. So you can go do the same thing, look at how are the security groups handled here. There's this Neutron open vSwitch input rule. You go to the next chain, and you jump a little bit back and forth, and it actually, you can verify that actually the packet will go through, and there is such a rule that allows it to pass. Okay, so it looks very complicated. That was my point.
It is very complicated. Okay, Tapio, thank you for taking us through that. So I think hopefully that gives the audience a flavor for the amount of stuff that has to happen in software to move packets back and forth through the data plane. And that's the critical reason why we need to offload to the SmartNIC. So let's talk about that. Let's talk about the SmartNIC. Of course, SmartNIC is a generic term. So we're showing the Giglio, which is the Neutron SmartNIC, here as a reference architecture. In the case of a Giglio, there are various data planes that we support, but here we're showing the OBS data plane offload technique that we have. So, briefly, really what we have here is on the server side, the compute node. You're running basically a standard implementation of Open vSwitch. What happens is the vSwitch user plane daemon will build the tables for the data plane, so match and action tables for the kernel data path in this particular instance. And those are then synchronized basically down into the SmartNIC. So the SmartNIC has all the information that is in the data plane, and the SmartNIC then accelerates in hardware. Basically the same exact operations that would have been processed, would have been performed on the server, are now processed in the SmartNIC, and the packets are delivered directly to the VNFs. That's the basic idea. And it's important to note here that from a control and orchestration perspective, this looks like standard OVS. So you're using OpenStack, and Open Daylight Controller in this particular instance. You can use other controllers as well, and they're all talking, with the standard protocols. No modifications are required there, and the SmartNIC is just basically forwarding packets at much higher rate, and then just as important, you don't require any resources on the server anymore to do the packet forwarding. So those are the main values here. Now this is showing a plain OpenStack implementation. We also have integrated with the OPNFV stack with the Danube release, starting with the Danube release, and I think Tapio, you're going to say a couple of words about that.
Yeah, thanks. So you may have been wondering what does all of this have to do with the OPNFV. So one exercise we did in the previous Plugfest in Paris, hosted by Morgan. Thank you. And so we had our own Nokia airframe hardware available in the meeting, and it was supposed to be a Plugfest. So we thought, okay, we're just plugging something. And the thing that we plugged in was this SmartNIC. And the guys from Neutron, they actually had they had the support already built for Danube. So we were trying the Neutron SmartNIC with the Danube software stack. And this Plugfest report came out this morning. You can take a look actually what happened in that. And here's a picture of our airframe hardware, and I think that's called the SmartNIC, right?
That is the SmartNIC, yeah. Not like me, that's the SmartNIC.
All right, so if you go to flip through the Plugfest report, you can jump immediately to the page which says performance and throughput, and that page is actually explaining the kind of testing that we did. And the only limitation that we did in this Plugfest, we didn't really have much time, so we're just using iPerf for doing the testing. And what happened with iPerf is that it's built on top of the Linux IP stack. And in this case, it was the iPerf running in a virtual machine that was the bottleneck. So Nick, do you happen to have any performance figures?
Sure.
That would be better than ours.
Yeah. So we have performance figures that we've harvested with the Agilio OVS, and this is showing the maximum data path performance. Now you can get to that maximum data path by running multiple iPerf instances to saturate the SmartNIC is one way, and then the other way is to use other tools, and we've run with all kinds of package end tools and testing tools to basically show that the data path can sustain upwards of 29 million packets per second with the SmartNIC accelerating the data path, and with basically just a single CPU core being used just to do some control and management of the data plane. So that's a pretty high number. The VXLAN performance is also pretty high. It's about 24 million packets per second, and that includes both VXLAN, NCAP, DCAP, as well as forwarding based on the L3 information inside the VXLAN tunnel. So those are high numbers, certainly compared to any kind of kernel-based vSwitch implementations. Even user space-based implementations, while being getting better all the time, are still significantly lower than that when you're talking about a single core performance. The other things to note here from a SmartNIC perspective is that the latency is dramatically reduced. The SmartNIC latency is about 5 microseconds or less when accelerating the virtual switch. So that's a lot less than the typical tens of microseconds, sometimes even 100 microseconds that you might incur going through a software-based virtual switch layer. And then the added functions that you can support, like the in-band telemetry, that's becoming very important and has a lot of value in troubleshooting problems between the virtual switch and VNFs. Very hard to get visibility on that if it's all on the server. With the virtual switch in the hardware accelerated, the SmartNIC can timestamp going in and out of the virtual switch, going in and out of virtual networking functions. So you can actually build nice information histograms of latency, where the latency problem is. If you have a service chain, you can actually see the latency through the different hops in the service chain. So if one VNF goes rogue, the latency goes up. You can see that, and then you can take corrective action. So these are all things that you can do. Obviously, QoS you can support in hardware with queuing, shaping, limiting, and so on, and things like crypto processing. So just an example of some things that you can do in the SmartNIC that are beneficial. So with that, I'll turn it over to Tapio just to talk about the use case.
Yeah, so question is what kind of use cases do we have for low latency? So I have two use cases in mind. One is core network, another one is the radio network. So OpenStack everywhere, like I said in a different interview. So as will be, I will say in a different presentation that we have this 5G radio, and like other vendors, we are starting to put this as much as the radio part also on top of the cloud infrastructure. And of course, the core network is already able to run on top of OpenStack network. So these are especially on the radio side where the latency, and especially with the 5G, where the latencies are very crucial, then something like this is very useful. And then that's not the only use case.
Correct, yeah.
You have.
Yeah, there's obviously many use cases. Basically, the higher the workload, the more important it is to have acceleration. So that's why radio is a great use case, especially as we move from 4G to 5G. The throughput's obviously going way up. So that's a big driver for SmartNIC, and of course, the latency becomes more and more important in 5G. So, but certainly the SmartNIC has use cases in all kinds of virtualized infrastructure and NFV in general. So yeah, real quick, just so you know what they look like and the different flavors, right? So you have, they're all standard PCIe cards, low profile, fit into standard COTS servers, various port speeds from 10, 25, 40, and we have larger cards with 100 gig on them as well. The software data plane is, software defined by the software image on the processor that's on the SmartNIC. That's why it's called a SmartNIC. So you can run different types of virtual switches like OBS. There's a core NIC load, which will just give you the basic NIC functionality. In some cases, you want that for compatibility purposes. We also have vRouter that supports the Contrail vRouter data plane. You can program the device also with custom data planes using languages such as P4 and C. And we're also, we talked earlier in the week about potentially doing a VPP data plane as well. So all of these things are possible. So getting back to tying this all together and how does this fit within OPNFV? Why are we at OPNFV talking about this? All right. We did do a big mini summit actually on Monday where we talked a lot about the data plane acceleration and VNF acceleration. The key point here is the data plane acceleration for SmartNICs. We just went through the value of that, and I think that that's generally accepted. I think the next step, once you understand that you can accelerate and open up that bottleneck, as we said earlier, then the VNF becomes the bottleneck of the whole infrastructure. So one of the things we talked about Monday at the mini summit about SmartNICs was that there's things you can do to accelerate VNFs onto the SmartNIC, right? Start pulling some of that VNF functionality into the SmartNIC. And one of the things that we've been discussing here at OPNFV that we're excited about is to develop an open API that would allow basically any VNF vendor to access an API, an open API, and access acceleration functions on the SmartNIC, right? And with an open API that the community agrees on, then we can have collaboration and we can have interoperability. Different SmartNIC vendors could go to the same API, right? So you have hardware independence and potential for a lot of collaboration. So we've been discussing possibly starting up a project within OPNFV to look at defining this API in kind of a collaborative and open way. So what do you think about that, Tapio?
Yeah, it sounds like a great idea. I think we can use sort of this data plane performance-focused project in OPNFV. Mm-hmm. And the idea is not to build something specific to Neutron on SmartNICs. The idea is to have an open API that supports different hardware. And there would be different sort of ways to offload functionality to the NIC, right? That's the
exactly. Yeah. I mean, the more people that use it, the better, right? So, I mean, we have to be open, and we have to have something that's easily usable, and that's the whole idea behind the open API. I should finish up by saying the other part of that is to create a test lab that would be kind of a community lab, so that we could have, let's say, SmartNIC hardware and infrastructure. VNF vendors could come, bring your own VNF, run it on the accelerated hardware, compare it to the unaccelerated hardware, and see what your gain is, right? Then you can do all kinds of neat things and TCO analysis and so on. So the lab is part of that suggestion as well. I encourage the audience to provide any feedback. There is an email on there at the bottom that you can get information. There's some documentation about concepts on the open API we can send to you. And there's also opportunity to get involved on the projects and contribute. So I encourage you, if you're interested in that area, to contact us at the email address there. So in closing, thank you all for coming, and I hope you enjoyed the presentation. Any questions? Mm-hmm.
I have one question about this, actually. The deployment is SmartNIC car is in the same virtual machine server, right?
I'm sorry?
I mean, the deployment is SmartNICs. It's in the...
You mean like the physical?
Yeah, physical.
Yeah, so, but it's just normal PCI card. That's how we used it in our hardware. That there's nothing, if that's the question. Or is the question, how do you see it from the virtual machine side?
Yeah, and from a virtual machine side, is that the physical location is the same server?
Yeah, it would be just the same. Well, do you want to take it?
But actually, I see that actually, if you do the migration, actually maybe had difficulty because you had this, for example, you had GDP tunnel, how you migration is the tunnel. You had GDP and different kind of protocol stack is proceeding in the smart car. And then if you do the migration, that you cannot do the might be difficult to migration those tunnels to another server.
Yeah. I mean, you can generally, you're saying if you don't have that capability in the target server where you're migrating to, is that your concern?
Yeah.
Yeah, I mean, that's always an issue, and you can solve that. Typically, if you implement the feature, if a provider implements a feature and wants it in SmartNIC, they'll have it in their OBS as well, right? They'll have that feature, so they'll have it, wherever they migrate it. If they're running a software-based OBS, for instance, in one server and a hardware-accelerated OBS in another server, you should be able to migrate between those two, as long as you're using some technology that allows migration, like VirtIO, for instance, which we support. then you shouldn't have no problem migrating between different implementations. In one case, it'll run faster. In one case, it'll run slower. But you should still be able to migrate VMs. Okay? Okay. Any more questions? Or?
Yeah, hi. Thanks. I have actually have 3 questions. So first one is like, so the statistic, I say you will do the statistic. So this statistic will be stored in the SmartNIC memory or host memory.
Right. So statistics will be stored in the SmartNIC memory for packets that are processed in the SmartNIC. That's
in SmartNIC. Right?
Yeah.
There's
yeah. And then they're synchronized typically with the OBS. In the case of OBS, they're synchronized with the OBS process in the server as well, because everything is managed, through the normal channels in the server. So there is a synchronization mechanism between local statistics in the SmartNIC and statistics in the host.
Okay, thank you. So the second question is like virtual machine to virtual machine communication. So that will pass the PCI bus. So do you have a number of the packet per second is instead of a bit per second number? Packet per second number?
Yeah.
For like a small packet?
Yeah, so that actually what I showed earlier was a packet per second number. So that was
packet per second.
Yeah,
okay.
that was almost 30 million packets per second.
30 million.
Yeah.
Okay.
30 million. Yeah.
Okay.
Yeah.
Thank you. So,
But yeah, I guess the PCI bus would be the bottleneck if you have a virtual
PCI
machine.
bus. Or PCI 3.
Yeah.
Okay.
PCI bus would only be a bottleneck from a bandwidth perspective if there were multiple hops, but there's of course depending on the bandwidth. If you're running a 25 gig, you got about 50 gig of bandwidth on the PCI bus, so you have some overspeed.
Yeah.
If you go from virtual machine to virtual machine,
Yeah.
the same host, and you go to the NIC, then it's obviously it's the PCI bus is the bottleneck.
Yeah.
That will be the limitation. It's not in the SmartNIC, right? The
I guess you
limitation.
can handle easily.
We can, yeah. And of course, you can go to higher bandwidth PCI. We're moving to by 16 or
You
multiple.
mean the current limitation is in the PCI, is not in the SmartNIC, right? The 30 million packet per second.
30? No, that is the data path. That's how many packets the SmartNIC data path can process.
Oh, okay,
Yeah.
got it.
Yeah,
Okay.
that's correct. Yeah.
Okay. So another question is like you have some security strategy and like defined in IP table rules. I say that how you offload that to OBS, change to OpenFlow rules or some other way.
Yeah. So we do have a package that offloads contract, which is starting in, I think it was OBS 2.5. There was that capability to have contract support with OBS.
Collection track?
Yeah, and that's what we offload with the SmartNIC, yeah.
But for IP tables, I think there are some rules to not only track the collection, it's about how to drop, it's not drop, it's match some field, right? So that will be translated into OpenFlow rules.
Yeah, anything that's in OpenFlow rules, we support. If it's security rules that are. Yeah.
So that part is already upstreamed into OBS, or you do that separate in another.
No, we support the functionality that's upstreamed into OBS.
Okay.
Yeah.
Okay.
Yeah, my example was a little bit misleading in that I tried to emphasize this old-fashioned way of having this Linux bridges between, because really what you should be doing with the standard OBS is to implement the security groups, the port filtering, the MAC filtering, things like that in the flows.
Okay.
Yeah.
Okay, thank you very much.
Yeah.
Okay. I don't know.
Question, please.
Okay.
I say your SmartNIC improved the performance a little bit, and will we consider that to use SmartNIC to do some, for example, VNF features like DPI or offload some?
Yeah.
I think
yeah. So we do have the ability to, as I said, touched briefly that you know, it's fully programmable, so you can start to program different functions into the device. We don't have any libraries or anything for DPI, you know, at the moment. So you know, you would kind of be on your own in terms of what you wanted to do there.
But I mean, this open API would be for that purpose, right? That you would offload.
If you, yeah, correct.
I mean,
that would be the model that I would recommend, right? Because if you had a DPI VNF, something like an IDS IPS application, then you could take pieces of that functionality and call acceleration, you know, functions in the SmartNIC, right? And so, for instance, you know, very good example is if your DPI application just decided that something needed to be blacklisted, you could program a rule into the SmartNIC to drop the traffic in the SmartNIC. It's a very simple operation, but it now saves the VNF from a huge amount of processing traffic, right, that just needs to get dropped. So that would be an example of accelerating a DPI application. But as far as actually doing inline DPI in the SmartNIC, we don't really support that, and that's, you know, that's not really the model that we're target kind of use case that we're going after at the moment. But yes, supporting a VNF that does DPI, yes, that would be applicable.
Okay, thank you.
And it will be the last question because we are already 10 minutes. Last question.
I have a question. You know, the SmartNIC can offload some a lot of packages, but if I mean, if for some service, it needs the package to keep in sequence. If some package need to deal with by the VM, for example, the fragment package need to be reassembled by the VM. So this package deal with by VM that will cause that the package cannot keep in sequence.
Yeah, so you know, the SmartNIC will keep packets that go into the SmartNIC and out of the SmartNIC in sequence, right? There's internal.
Except possibly for the first one, before you establish.
Right. So within, yeah. So there is some flow establishment which you know, theoretically could result in a resequencing of some packets, but through the SmartNIC it stays in and out. This would be through the control plane. But I'm not sure what your question is on that in that respect.
I can give an example. For example, there are 10 packages received, and some packages was offloaded by the SmartNIC, and a few of packages were dealt with by the VM. I think that it's impossible to keep the 10 packages in sequence, because when some packages deal with by the VM, we cannot keep the package in sequence.
Yeah, maybe we should discuss that offline. Why don't we not keep the whole audience
Yeah,
here?
I think we'll run out.
Come on up and we'll talk about it.
Thank you.
Thank you.
Thanks, Morgan.